Alright guys, welcome to lesson 5.12.
It's our last lesson for Unit 5. We're going to do some word problems now where we find maxes and mins. And these are called optimization problems. So, what is an optimization problem? It's a word problem in which we determine the highest or the lowest value possible in a given scenario. So here's an example of a particular kind of problem that we'll be looking at later today. Suppose you have 100 feet of fencing and you're making a rectangular region that you want to fence in. So the question is, how should you arrange the fencing so that you cover the greatest possible area? All right. Why is this important? In the real world, we often desire to have the max or min of a given product or outcome given certain constraints. Okay, so for example, suppose you are designing something and you want to use the most material possible without wasting it. Or you want to maximize your profit or minimize your costs. So these are all types of optimization problems. So here are the steps, and we're going to be using these steps throughout the day. There are 5 of them. In these problems, typically you're going to have a primary equation and a secondary equation. The primary equation is the equation that has the variable in it that you're trying to optimize. So for instance, if you were trying to optimize the area of a rectangular region, well then the primary equation would be the equation that has a formula with the area involved in it. Now a secondary equation will happen on some of these problems. And for these types of problems, you're going to have a secondary equation because there's things within the problem that restrict it. So I mean, for instance, if you had an infinite amount of fencing available and you wanted to make a rectangular region with the fence, well, with an infinite amount of fencing, there is no limit to the amount of area you could cover, right? But, you know, if you only had 100 feet of fencing, well, now you are constrained. You have some restrictions on what your possibilities are. And so maybe you want to find what's the maximum area. That's the primary equation. But how much fencing you have would be another equation that we have to incorporate within the problem because it puts a limitation on our possibilities. Okay, so typically you're going to have both a primary and a secondary equation. There are some types of optimization problems where you don't need a secondary equation simply because the first condition, the first equation that you have, already has some limits built within it, and so you wouldn't need a secondary equation to put limitations on it. But for the most case, we're going to have 2. A primary equation, which contains the variable we're optimizing, and a secondary equation, which puts limitations on our possibilities. Once you have those 2 equations, the next thing you're going to do is in the secondary equation, you're going to want to get one of the variables by itself. Now, it doesn't really matter which one you get by itself. My suggestion would be, though, to get the one by itself that makes the less ugly looking outcome as a result. And we'll see a couple of examples of that today. Once you've done that, and you're going to plug it in to your primary equation. So now you end up with only one equation and with only one type of variable involved. And so that's why we do that. So it's kind of like a system of equations. And we're doing the substitution method. Well, anyway, so after we find our primary, we find our secondary, and we put them together into one equation that's a little bit simpler because it has fewer variables. The next thing we're going to do is we're going to actually find the minimum and maximum values of that new equation that we created. It's kind of like doing the candidates test, only it's going to be a little bit less work than that because with the candidates test, you usually get a whole bunch of possibilities. But really with this particular type of problem, you're really going to end up with just getting one answer. And there are exceptions to that, but not for the types of problems I'm going to be giving you. You do want to make sure at the end, of course, anytime you're doing word problems, that your answers are reasonable and within an acceptable domain. But for the most part, steps 1 through 4 will cover our tracks pretty well. As in the case of almost any time you do a word problem, some things you want to keep in mind is make sure you pay attention to what it's asking for. You know, sometimes in the process of solving an equation, you'll get the answer for x, but they're asking for y. So sometimes after you get x, you got to go back and find y or something like that. So pay close attention to what they're asking. And here's some common types of optimization problems. Now, we're not going to be getting to all of these today. In fact, we're only going to cover about 3 types of problems. It would be wonderful if you could take these 3 types and kind of develop an ability to solve a variety of type of problems. But in reality, you know, it's okay. I'm only going to expect you guys to know 3, and it's just to kind of give you guys some exposure to optimization problems. So really common types of optimization problems are problems that involve finding what makes the most or the least amount of volume, or what makes the most or the least amount of area, or what makes the distance the greatest or the smallest. And very often it involves putting shapes inside of other shapes and things like that. Those are really common types. We're only going to look at 3 types today. So let's go ahead and jump in and take a look at our first type of optimization problem. It's the Cryptology Question. I like to start off with this one because it's one of the easier ones. So let's go ahead and see how this thing works. So let's read it here first. A cryptographer expert. Now, cryptographer, I would assume, is somebody who is an expert in making secret codes or something like that. A cryptography expert is deciphering a computer code. To do this, the expert needs to minimize the product of a positive rational number and a negative rational number. So we're minimizing the product of a positive rational number and a negative rational number. Given that the positive number is exactly 6 greater than the negative number, what final product is the expert looking for? All right, so how do we know that this is an optimization problem? It's because they're asking us to find a minimal amount. So that's kind of your cue right there. It could also be if they were asking for a maximum amount. But that's kind of like your red flag to say, uh-oh, we're dealing with an optimization problem. All right, so step 1 is to identify your primary equation. Now, as I mentioned in the beginning, the primary equation is what you're trying to minimize. What am I trying to minimize? I'm trying to minimize the product of a rational number that is positive and a rational number that is negative. So I'm going to put P for product. The product of a rational number that is positive, what should we put for that? I guess I'll just put R. And another rational number that's negative, for that one I'll put N. Okay, so we might want to label these positive rational number and negative rational number. So the product of a positive rational number and a negative rational number. That's my primary equation. Okay. Now we're going to look for our secondary equation. And remember, the secondary equation is the equation that puts some limits on this. You know, what are the limits that they're giving us here? Well, it's right here. It tells us that you can't just pick any 2 numbers. You're kind of restricted to a certain group of numbers. The positive number has to be 6 greater than the negative number. So the positive rational number, which is R, is 6 greater than the negative number. So we know that R has to be equal to 6 plus N. So my primary equation, the one I'm trying to minimize, is P equals R times N. My secondary equation, the one that restricts our possibilities, is that the rational number has to be 6 more than the negative number. All right, now for step 3, what we're going to do is we're going to do the substitution method. I didn't write it like that in the steps above, but that's essentially what it is. In the substitution method, you want to start by getting a variable by itself in the secondary equation. So you take your secondary equation, and you want to get a variable all by itself. Now I've already got that, so on this one I don't have as much work to do as I might on others. I've already got r by itself. I can see that r equals 6 plus n. And what we're going to do is we're going to substitute that into the other equation there. So since r equals 6 plus n, I'm going to plug 6 plus n for r. And then I'm going to simplify that. Okay, so that's step 3. Step 1, identify your primary equation, the equation that you're trying to minimize or maximize. Step 2, identify your secondary. Step 3, use the process of substitution to rewrite your primary equation so that it no longer has 3 variables but only 2. Okay? All right, so now we're going to move on to step 4. Step 4 is to actually find the minimum of that new equation. Now, it could be finding the max technically, but in this problem, we're looking for the minimum, so I'm just going to put find the min. So we find the derivative of p with respect to n. So it's going to be p prime. If you wanted to, you could write dp dn, but I think just to keep things simple, I'm not going to. But I'm just saying that just so you guys know it, we're finding the derivative with respect to n. So it's p prime is equal to 6 plus 2n. And to find the minimum, we're going to set the derivative equal to 0. That helps us find critical values. And it's at critical values that we typically can find our relative extrema, right? And then we solve. And I end up with a negative number that is negative 3. So there's that. Now, I would stop here if the problem was asking me what's the negative number, because the negative number is negative 3. But the question is asking us what final product is the expert looking for. So they don't want to know what is n, they want to know what's p. Okay, so to find p, we also need to find r. Once we know what r is, we can multiply it by n, and that will tell us what p is. Okay, so how can I find r so that I can also find p? Well, once again, you're going to go back to your secondary equation at this point. And I still am considering all of this to be part of step 4, really. You're going to go back to your secondary equation, which is r equals 6 plus n. And you're going to plug in the number that you found so far. So now we know that n is negative 3, which tells me that r is positive 3. So my positive rational number is 3. My negative rational number is negative 3. And now I can answer their actual question, which is given by the equation p equals r times n. So the product is equal to the positive rational number multiplied by the negative rational number, which is negative 9. And that's the final answer right there. And so just to be more clear, I'm going to unbox this because these are not the answers it's looking for, but we did need to get those to get to the final answer. So step 1, identify your primary equation. Step 2, identify your secondary. Step 3, do substitution. Step 4, find the minimum and find all the possible variables you can. And step 5, make sure that your answer is the one that they're actually asking about, and then it's a reasonable answer. And there we have it. So that is example 1. Now, instead of giving you guys a student practice, I'm just going to let you guys do your homework simultaneously here. So pause the video here and go open up your homework assignment and do number 1 on your homework assignment. I'll leave it to you guys to check your answer on the answer key, and then if you didn't get that answer, we can chat about it in class and see what might have went wrong. Let's go ahead and move on to example 2. A rancher wants to construct 2 identical rectangular corrals using 500 feet of fencing. The rancher decides to build them adjacent to each other so that they share fencing on one side. What dimensions should the rancher use to construct each corral together so that they enclose the largest possible area? All right. For these types of problems, I'm going to recommend that you draw a picture first. Anytime there's geometry, pictures are nice. So I'm going to encourage you to pause the video here and see if you guys can draw a picture of what this corral would look like. Just this shape. You don't have to put numbers on it yet, but just the shape. What would it look like? Well, he says that he is drawing, he's creating 2 identical rectangular corrals, so they're rectangles, and they're put together so that they share a side. So when I visualize this, I see 2 rectangles put together, and they're the same exact size. So 2 congruent rectangles joined together at a common side there, right? And it's going to be helpful to us to label these a little bit. I'll call this A. So this also would be A, right, because they're equal. And I'll call this B. I guess we could call this B also, and B, and A, right? There we go. So we're going to need those in a minute. But for now, draw a picture. Now we can actually begin our steps. So let's identify our primary equation. So what am I trying to minimize or maximize? Well, it says here we're trying to create the largest possible area, right? So I want to create the largest possible area. Well, how do you find the area of this shape? Well, as you guys know, the area of a rectangle is base times height, right? So we have base times height. So my base is 2 A's put together, and my height is B. Matter of fact, I think I'll just rewrite it like this. So, but there you go. So there's your primary equation. That's the equation I'm trying to find the minimum and the maximum of. Let's move on to step 2. In step 2, we need a secondary equation. The secondary equation is, what is our limitations here? Well, in this case, they're only giving us 500 feet of fencing. So how can I turn that into an equation? Well, all these lines added together, that one, that one, that one, that one, that one, that one, and that one, all those lines added together represent the fences, right? If we put all those together, it should make a total of 500 feet if we use all the fencing, right? Well, as you guys can see, there's 4 A's there, and there's 3 B's. And that should all add up to make 500. So that's our limitation. We're only allowed to have 500 feet of fencing. Okay? All right, let's go ahead and move on to step 3, substitution. So we start with our secondary equation, which is 500 equals 4A plus 3B. And what we want to do is we want to get one of the variables by itself. Oh, I wrote that wrong. It's supposed to be 3B, not 3A. We want to get one of the variables by itself. Now, it doesn't really matter which one you get by itself. So let's just say that we want to get A by itself. So the first thing I would do is I would subtract 3B on both sides. And then I would divide both sides by 4. Maybe I'll just leave it as one big fraction. There we go. So I've got A by itself now. Now you could have gotten B by itself. It really doesn't matter. So long as you get one of the variables by itself. We're still not done with step 3 though, substitution. The first thing you do in the substitution method is you get a variable by itself. The second thing you do is you plug it into your primary equation. My primary equation is A equals 2AB. What am I going to plug in, and where am I going to plug it into? I'm going to plug 500 minus 3b over 4 in for A, because that's what A equals. So I'm going to continue my work over here. So if I did that, I have big A, which represents area, is equal to 2 times the little a, which we now are replacing with 500 minus 3b all over 4. And then there's the b. All right. And we want to simplify this a little bit. So first of all, I might reduce the 2 into the 4. And also I might distribute this b into the top. And so here's my outcome. I have 500b minus 3b squared all over 2. All right. And now I'm also going to split these up a little bit now. I'm going to do 500 over 2b minus 3 over 2b squared. And the reason I'm choosing to write it like this is because it's going to make the derivative in step 4 a little bit easier. And also we can see here that 500 over 2 can be simplified into being 250. All right. So now we move on to step 4. In step 4, we're going to find the minimum or maximum. In this case, the problem's asking to find a max, so we're going to find the max. Right. So to do that, the first thing we do is we find the derivative of A with respect to B in this case. So the derivative of A with respect to B is going to be 250 for the first one. If you take the derivative of 250b, you get 250. And if you take the derivative of this one, you're going to multiply 2 to the front, and 2 times negative 3/2 is just going to leave us with 3. And you take 1 off of the power, so we have that. And then we set the derivative equal to 0 so we can find the critical values. I'm going to add 3b to both sides. And then I'm going to divide both sides by 3. And I end up with a b value of 250 over 3. All right, now the problem is asking us what dimensions should the rancher use? In other words, what is both A and B? So what is both A and B? And it says for each corral. So, you know, we have 2 of those corrals, right? And they both have the same dimensions, A and B. So we just need to find basically A and B. We've already got B, so I'm going to circle that. That's an answer we want to keep. And now we want to find out what A is. So once again, to find the other variable, you're going to go back to your secondary equation, and you're going to plug in the one number that you do have so you can find the other number that you don't. So here's my secondary equation. It was 500 equals 4A plus 3b, and we just figured out that b was equal to 250 over 3, and that's pretty convenient because those 3's just cancel out. Might not always be that convenient, but in this case it is. And then we're going to subtract 250 on both sides, and then we're going to divide by 4. And that can be reduced, so I would say 125 over 2 for A. And there's our dimensions for those corrals. Okay? Is that a reasonable answer? Sure, why not? It works. It's positive. You wouldn't want to get a negative one, right? That'd be weird to say that the corral has a negative length to it. So these answers are reasonable. Now, a question might come up at this point. Says, Mr. Bailey, when you're doing this process over here to find the minimum and maximum, when you set the derivative equal to 0, that finds you critical values. And you said that critical values could be a relative min, a relative max, or neither. So how are you sure it's a relative max? Well, technically, we're not sure of that, but I can guarantee you with the problems, it's going to be either a minimum or a maximum. Now, your question might be, well, how do you know it's not a minimum instead of a maximum? Well, if you only get one answer, then that's got to be the one, right? So that's pretty much how this is always working out. Now, if you get two answers, you could legit do the old school candidates test, right? You could put all your possibilities over here for x, right, your inputs, and then you could put over here all the different possible areas and see which area actually comes out to be the greatest. But honestly, I'm not going to give you any questions that are like that, so just so you guys know, on step 4, if you just find the derivative and set it equal to 0, you're going to get the answer that they want. But yes, technically, doing this could give you a min, a max, or neither. And so technically, you should be doing the candidates test to make sure. But I'm telling you, for the problems I'm giving you, just setting it equal to 0 and solving, you're going to get the answer that they want. Now, for you guys, I want you guys to pause the video here and do your homework problem number 2. Now, on your homework problem number 2, it is slightly different than mine. It doesn't say that we're putting two corrals next to each other like this. Instead, it says that you've got a wall that already exists. It's a stone wall, and you're using fencing like this. And what's important as you guys are doing that homework problem is you understand that your fence is not here. You don't need a fence here. So really, when you're finding your secondary equation will only have those 3 components to it. It's not going to have the same thing I did. So go ahead and see if you guys can do that homework problem. Check your answer on the answer key. When you're all done, come back and let's take a look at example 3. If you didn't get the same answer as me on the answer key, we'll talk about it in class. Let's move on to our last problem here, example number 3. All right. The designer of a cylindrical can of soda wants to design a soda can that can hold 145 pi cubic centimeters, which is approximately 16 ounces, but for our problem, I didn't really want to focus on ounces. I wanted to focus on something a little bit different. I wanted to do cubic centimeters. It makes the rest of the problem easier. So we're designing a cylindrical can, and in this can, it has to hold 145 pi cubic centimeters of fluid. But at the same time, the maker of this can wants to make sure that he or she is reducing the amount of aluminum that they need to make the can, because that'll make production cheaper. You don't want to spend more money than you need to, right? So the question is, what is the minimum amount of aluminum that the designer can use to hold this much fluid? All right, so now this problem's a little bit tougher. On your homework problem that corresponds to this, yours is going to be a little bit easier, but I just want to kind of give you guys an extra example to look at. So the reason why this one's a little bit hard is because we're dealing with a cylinder, but on your homework you're dealing with a cube. Cubes are much simpler than cylinders. But here we go. So what is my primary equation here? Well, that's the one I'm trying to minimize. So what I'm trying to minimize is the amount of aluminum I need. Now what's confusing about that is you have to know what that corresponds to geometrically. The aluminum is the outside part of the can, right? In other words, it's the surface area of the can. So what is the surface area of a cylinder? The surface area of a cylinder is found by finding the area of the top. Now, that's a circle, right? With a radius of r, we'll say. And the area of a circle is pi r squared. But there's 2 circles, isn't there? There's also one on the bottom. So there's 2 pi r squared. But we also need to calculate the surface area of the side. Now, if you guys can imagine unwrapping this can, it would look like this, like just making a slit down the height. There's the top, there's the bottom. If you cut this thing down the side here and unrolled it, it would be a rectangle, wouldn't it? So the question is, how long is this length here, and how long is the height? Well, we don't know what the height is, but we do know it's going to be base times height. Now, we know something else, though. We don't want to make this harder than it needs to be by having too many letters. This base, actually, we can know what that is. The base is exactly the length of the circumference of that circle. So the base is actually 2 pi r. So instead of base times height, I'm going to do 2 pi r times height, because the base of this rectangle is equal to the circumference of the circle on top, and the circumference of a circle is 2 pi r. All right. Now, that's what makes this problem a little bit harder, is that I'm giving you a weird shape, and calculating these things is a little bit harder. For your shape, it won't be quite as hard, but it will make you think a little bit. But there's my primary equation. I'm trying to minimize the surface area of this cylinder. I'm trying to create the least amount of aluminum possible needed so that I can minimize my costs. But my secondary equation, what's the limitation on this? Well, the limitation is that the volume has to be this much. I don't get to play around with that. It has to hold that much fluid. Okay, so how do you find the volume of a cylinder? Well, the volume of a cylinder is the base of the cylinder, which is a circle, the area of the base, which is pi r squared, multiplied by the height. Okay? So that's, in my opinion, that's what makes this problem a little bit trickier than the one you have, is just getting these first two equations. Matter of fact, if you were actually taking the AP exam, they might just give you these formulas. I'm not sure. I won't be throwing anything at you on your test where you have to create stuff this much off the top of your head. I will, and if it is that complicated, I'll at least give you the formulas so you know what they are. But anyway, there you go. The primary equation is the surface area. The secondary equation is the volume, and we know the volume is 145 pi cubic centimeters. All right, so now we're ready for step 3, which is substitution. So what do we do with step 3? We take the secondary equation, and we get one of the variables by itself. You could get either r or h by itself, but what do you guys think would be much simpler to get by itself? I hope you realize it's h. It's a lot easier just to divide both sides by pi r squared, and as soon as you've done that, you've got h by itself. Also, these pi's cancel out. It's much easier to get h by itself. If you tried to get r by itself, you'd have to divide by pi and h, and then you'd have to take a square root. And square roots are ugly. Let's not deal with it if we don't have to, right? So there's that. So my height is that. So now we're not done with step 3, though, right? After you do the first part of step 3, which is to get a variable by itself, then you come back to your primary equation and you plug that in. So I'm going to plug 145 over r squared into my primary equation for the variable h. If I do that, it would look like this. All right. And we could probably simplify that a little bit. So, for instance, we could do 2 times 145, and we can also probably just put the pi on the top as well. And then this r will cancel one of the r's off the bottom. And so that leaves me with the following then. right. So now we're ready for step 4. In step 4, we want to find the minimum. So we're going to start by finding the derivative, but before I do that, I want to make my equation derivative friendly. I don't like that 290 pi over r, so I'm going to rewrite as 290 pi r to the negative 1. That way I can just do the power rule on it instead of the quotient rule, which is much easier. Now I'm going to find my derivative. Power rule, we're going to multiply 2 to the front and take 1 off of the power. Power rule again, we're going to multiply negative 1 to the front and take 1 off of the power. And that leaves us with the following. Now that the derivative's over, I'm going to go ahead and put that r squared back in the bottom. So now we want to find the actual minimum or maximum. So what we're going to do is we're going to set this thing equal to 0. And I would start by adding 290 over r squared to both sides. Then I would multiply both sides by r squared so that these cancel out. And then I would divide both sides by 4 pi so that these cancel out. The pi's go away, and 290 over 4 can reduce to 145 over 2. And then what I would do is I would take the cube root of 145 over 2. Now at this point I'm just going to use my calculator because I don't want to leave it like that for my rest of my calculations. It just kind of is going to be a bit of a pain in the butt to have a cube root in there. And if you guys don't know how to do a cube root, some of your calculators have a cube root button, but you can also raise it to the 1/3 power. It's the same thing. So if you just take the fraction 145 divided by 2 in parentheses, and then you raise that to the power of 1/3 in parentheses, that's the same thing as taking a cube root. And I'm going to get out of that 4.170. And just remember, in calculus AP, we like to round to the thousandth place every time. Okay. So there's r. So I just found the radius of my can that would have a minimum amount of material used. The radius would be 4.17. Since we're talking about centimeters here, it would be about 4.170 centimeters. Now we're not quite done here. We need to actually find the minimum amount of aluminum. In other words, they want to know what's the surface area. Okay, so now there's 2 ways you can go about doing this. And one way is you could find the H. You could find the H by going back to your secondary equation and solving for H and then plugging it into your original primary. Or we could just use this one. This is also a surface area formula, it's just that it has the H taken out of it. So I think I'm going to go ahead and go with that one just to kind of make things go a little bit faster. But the point is they want to know the surface area, which represents the amount of aluminum you're using. So for step 5 or 4, continued, we're going to do 2 pi and then 4.170 squared plus 290 pi over 4.170. And then once we calculate that whole thing out, we'll have our final. And I get 327.738 square centimeters. Remember, we're talking about areas, so that's why I put square centimeters. So you got to pay attention to your units, like radius will just be centimeters. Area is going to be square centimeters. If you're talking about volume, that's cubic, right? So pay attention to those units. But that's not as big of a deal, but that's the basic outcome there. So at this time, you guys, you're going to do a volume problem also, but you are going to have something a little bit simpler. It's going to be the volume of a cube. So go ahead and do your last homework problem, number 3. This video is over. Check your answer on your answer key for your homework to make sure you got the correct answer. If you didn't, once again, we'll chat about it in class, and we'll see you guys next time.